Good morning again, everybody. We're going to go ahead and get started. As usual, since we have an exam this week, I've got some exam review questions. There's a couple of review questions that we didn't get to last week, and then I pulled a few more from the exam review that's been posted on Blackboard. So if you had a chance to do this first question, we're looking at whether or not a precipitate will form with the following reactions. So these are double replacement reactions. And remember that with double replacement, the ions switch. So magnesium is with the sulfate. When you mix those two aqueous solutions, the magnesium will now be paired with the magnesium chloride. And then likewise, the sodium will switch as well. And so the question here is, are either of these two things solid, or are they both aqueous? We use the solubility rules, which I posted here, and you'll have access to these. And what you realize is that both of these are aqueous. So there's no reaction. For the second one, when you switch ions, you make silver iodide and you make strontium acetate. All acetates are soluble, so that's aqueous. Halides usually are soluble too, but silver is an exception, and it is insoluble. So this one, there will be a reaction. You're going to form a precipitate, and it's going to be silver iodide. Are there any questions on this one? Because sometimes the predicting the precipitate ones are a little tricky. If there were no questions, how did we do? I know it's early, y'all, but talk to me. You know how it works. This exam review is for y'all, not for me. So practice using those solubility rules. Here's the next question. Predict whether each of the following metals will react with sulfuric acid. And I gave you the relative activity series down below. So you can just write react or no reaction, and that'll be fine. So I'll give you a couple of minutes to look it over and do the problem, and then I'll check back in. Alrighty. So for A, we have silver. Will silver react with sulfuric acid? No, it's not going to react with sulfuric acid. So here's hydrogen. Here's silver. Silver comes after hydrogen on the relative activity series. So there's going to be no reaction. What about tin? So you're looking for where tin is relative to the hydrogen. Tin comes before hydrogen, so that means it's more reactive, so it will react. So were people stuck on this one? You gotta let me know. If you're stuck, let me know. So you find where the metal is in reference to the hydrogen. If it comes before, it's more active, so there will be a reaction. Is cobalt going to react with sulfuric acid? Yes. See, now if y'all would have said something, we could have figured that out a long time ago. Good morning, y'all. Come on. I know it's early, but you gotta let me know. What about manganese? So all of them will react except for silver. Questions on that one, or are we ready to move on? Here's a gas density question. So I'll give you 3 minutes to read it and get started, and then I'll start solving it. Are we ready to go over it, or do you still need some more time? All right. So with this one, we're talking about gas density at STP. Now we have two definitions of density. Density is always equal to the mass over the volume. Whether it's a gas, a solid, a liquid, doesn't matter. We also have, for gases only at STP, that the molar mass divided by the molar volume is also equal to density. In the problem, we have a mass of 25.4 grams and a volume of 15.9 liters. We're asked about what the molar mass is, and we can figure that out if we use this proportion. And remember, I abbreviate molar mass with mm. And the molar volume is always equal to 22.4 liters. That's the volume that 1 mole of gas occupies at STP. So with this setup, you can solve for the molar mass. and you should get something in the ballpark of 35.8 grams per mole. How'd we do on this one? For those of you who are not speaking up, if you don't tell me how you're doing, I won't know. So if you need something explained, you gotta speak up. But I'm glad there are a few of you who are chiming in and you did all right. Okay, good. Let's move on to the next one. This is another chapter 8 question. So we have mercurious chloride. We know the molar mass and its percent composition. You have to figure out the molecular formula. I'll give you 4 minutes to start on this one, and then I'll chime in. Alright, we can start going over this one. If you're not done yet, that's fine. You can keep working. So with this kind of question, we're going from percent composition to the empirical formula to the molecular formula. In order to go from the percent composition to the empirical formula, we have to make an assumption. And that assumption is that we have 100 grams of substance. That way, instead of percent, we can say grams for each of the elements. For each of these, we're going to take the number of grams and convert to the number of moles. That uses the molar mass of each of these. So are we good so far? Alright. Now that we have our number of moles, we can figure out what our empirical formula is. When we look at our ratio, we've got 0.424 moles of mercury for every 0.423 moles of chlorine. That sounds like 1-to-1 to me. This means that our empirical formula is HgCl. But we're not there yet. But did people get this far to find the empirical formula? And if you got stuck, you can let me know that too. Okay. The next part is taking that empirical formula and going to the molecular formula using the molar mass. We first have to calculate the molar mass of the empirical formula. So you should get somewhere in the ballpark of 236 grams per mole. And that's what we're going to use to figure out our N. You take the molar mass of the substance, which is given in the problem, and divide by the molar mass of the empirical formula. That gives you about 2. It's like 1.99. That's 2 in my book. So that means we're going to multiply our empirical formula by 2. And this is our molecular formula. Questions? Yes. Are you talking about the empirical formula part? Yeah, I just did that just to show that's how you do it. If they weren't 1-to-1, then you'd have something other than 1 for, for the ratio. But you can still show the division. Other questions? Alrighty. Then we're going to keep moving on if there's no questions. So you have a mass of ethane gas, and you have to figure out the volume of the gas at STP. I'll give you 2 minutes, and then I'll start setting up the problem. I'm going to start setting up this problem here. We've got a mass of 7.5 grams of ethane gas. And the question is asking us about the volume. We can't just go directly from mass to volume. We've got to go to moles in between. To go from mass to moles, we're going to need the molar mass of ethane gas. I'm not going to write out how I got it, but if you don't understand how to calculate molar mass, please let me know. Essentially, you just add up all of the masses of the atoms that are in the molecule. So that's how I got the 30.068. You should get something in that ballpark, about 30. Your molar mass may vary a little bit depending on which periodic table you use. For the second part of the problem, where you have to take the number of moles and go to volume, you need to use molar volume. And that's for gases only. One mole of gas occupies 22.4 liters. So that's the unit equation for molar volume. So our first part is going to be converting from mass to moles. And then the second part, we're going to use that molar volume. Make sure that your units cancel. So we can cancel grams because there's one on the top and one on the bottom. We can cancel out the moles, and we're left with liters, which is good because we're trying to find a volume. Did anybody get an answer for this one? And if not, you can put this in your calculator and give it a try. Let me know what you got for this. I got 5.59 liters as well. Any questions on this one? Okay. So that's it for the exam review. We did some questions last week, and then we did some more this week. There's the exam 4 review that's posted, and the answer key is also posted. So you can work your way through that, and then if you have questions, you can always come to office hours. In terms of exam 4, I decided that it's going to be a take-home exam. So it's open note, and you can do your exam, just do it by yourself, because I want you to be able to show your work and show me what you know, versus doing a multiple choice exam and trying to upload your work. I think a take-home exam would be more beneficial to you guys than doing a traditional respondus lockdown exam. So again, exam 4 on chapters 7 and 8 is going to be a take-home exam. So you can use your notes, but you must show your work. The exam will be posted on Wednesday, which is the 28th. You need to upload your answers with your work Friday, October 30th by 11:59 p.m. So if you do not upload your responses and your work, then you don't get credit. So it's got to be there before the end of Friday. Are there any questions about that? All right. Today we're starting chapter 9, and we're doing some more math. So if chapter 8 with the mole calculations was difficult, then chapter 9 will also be difficult until you get those chapter 8 problems worked out. So if you are struggling, if you feel like Chapter 8 was really, really difficult, please reach out. Get a tutor, talk to me, work with a friend in class, but don't just get left behind. We're going to cover Chapter 9 over the course of 2 weeks. So I wasn't super concerned about you guys watching the video before we got started. It'll be fine. We'll finish up whatever we don't do next week, along with some more practice on these Chapter 9 problems. Before we start doing the real math, let's talk about how you can interpret a chemical equation. Let's say that we have nitrogen gas and oxygen gas combining to make nitrogen monoxide, and this reaction requires heat. Remember that there's coefficients in front of these, and if there's no coefficient, it's a 1, right? So if I have one molecule of nitrogen gas and one molecule of oxygen gas, I can make 2 molecules of nitrogen monoxide. Pretty simple. We can say the same thing with moles. If I have 1 mole of nitrogen gas and combine it with 1 mole of oxygen gas, I can make 2 moles of nitrogen monoxide. So the coefficients can be used to talk about the number of moles of each reactant and product. But it has to be a balanced equation. We're going to talk about something called mole ratios in a minute. Now notice how all of these reactants and the product, they're all gases. With gases, at the same temperature and pressure, we can also talk about volume. So if you had 1 liter of nitrogen gas and 1 liter of oxygen gas, you can make 2 liters of nitrogen monoxide. But this is only when we're talking about gases at the same temperature and pressure. Is everybody good with that? That we can take those coefficients and just say that they're moles, and we can relate them to one another using the chemical equation. From that balanced chemical equation, we can write mole ratios, which we can then use as unit factors to do math. A ratio is just one number, it looks like a fraction, right? So it's one number over another. If I wanted to write mole ratios for the nitrogen gas and the oxygen gas, I would simply look at the chemical equation and see what the coefficients are and write it out as a fraction. We've got 1 mole of nitrogen gas and 1 mole of oxygen gas. That's a mole ratio. The other mole ratio is the reciprocal. We're literally just taking the coefficients from the chemical equation and writing them out as fractions to show how they're related to each other. Take a second and tell me, what's a mole ratio that we can write that shows the relationship between oxygen gas and nitrogen monoxide? Yeah, it's got to be 1 to 2. So look at the coefficient in front of the nitrogen monoxide. There's a 2. So that means we have 1 mole of oxygen gas for every 2 moles of nitrogen monoxide. There's always 2 mole ratios. So you write 1 and then you write the reciprocal. If we wrote mole ratios for nitrogen gas and nitrogen monoxide, it would look pretty similar to the ones for oxygen gas and nitrogen monoxide. We've got 1 mole of N2 for every 2 moles of NO. That's mole ratios. I'm going to let you guys do a little practice. Here's a new chemical equation. I want you to write the 2 mole ratios for mercury 2 oxide and mercury. You can throw one of them in the chat if you'd like. So it does reduce down to 1 to 1, but you don't want to reduce it like that. You can just leave it exactly as it is. So you literally take exactly what the coefficients are. You don't have to simplify. So that would be 1, and then you flip it for the other. And while the number is still the same because it's 2 to 2, when we're talking about using these as unit factors, it matters to have both. Let's do a little bit more practice. So write 2 mole ratios for the mercury 2 oxide and oxygen gas. Yeah. So you've got 2 moles of the mercury 2 oxide for every 1 mole of oxygen gas, and the reciprocal, 1 mole of oxygen gas over 2 moles of mercury 2 oxide. Writing mole ratios and being able to choose the right one to solve the problem, that's one of the key points for chapter 9. So just like with the other things that we've been doing in chapter 8, choosing the right unit factor makes all the difference in getting the right answer and not. So let's show how we actually use these mole ratios. How many moles of oxygen gas are produced when 3.50 moles of mercury 2 oxide are decomposed? Here we've got a mole to mole calculation. We have moles of one thing. We're trying to convert to moles of another using the chemical equation. The first thing that I like to do is write out what I have and figure out what units I'm trying to get to. What we're given is the moles of mercury 2 oxide. The question is asking for how many moles of oxygen gas. So for this, we're going to need a mole ratio between the mercury 2 oxide and the oxygen gas, just like we did before. So we wrote out those two, but now we need to figure out which one to use. Where should I put the 2 moles of mercury 2 mercury 2 oxide? Should it be in the top or the bottom? It should go in the bottom. What goes in the top? The 1 mole of oxygen gas goes in the top, because this is our mole ratio. And we're trying to figure out how much oxygen gas we make when we make 3.50 moles when we decompose 3.50 moles of the mercury 2 oxide. So figuring out that mole ratio is key. And just like with all the other calculations we've been doing, you can always make sure that your units cancel and that you're getting the units that you want, which is why I like to rewrite the question. We're looking for moles of oxygen gas, and that's what we have. I have some more practice for you. So are there questions on this, or do you want to try one yourself? Go for it. I can answer that in 2 ways. The first way is the one that goes on the bottom is the one you're trying to cancel out. We're trying to get rid of the moles of mercury 2 oxide, and that's in the top right now. To cancel it out, you need to have it in the bottom. The other thing is that if you set up the problem like this, where you write out your given and your question, then your mole ratio will always look like this. Whatever the units are in the question will go on top. The units in the given will go on the bottom. But that's only if you set it up like I do. Other questions? Or are you ready to try it yourself? Then try this problem. Still the same chemical equation, but we're just dealing with some different numbers and different compounds. So I'll give you 2 minutes to work on it, and then I'll set it up. I'm going to start setting up the problem. So the question is asking how many moles of mercury 2 oxide decomposed to produce 5 moles of mercury. We're starting with 5 moles of mercury and trying to figure out how much of the mercury 2 oxide we started with. For our mole ratio, we've got 2 options. Which one of these are we going to use? We're going to use A. So just like I was saying before with this one, we were just writing out the mole ratios. 2 over 2 is going to give you 1, no matter which way you slice it. But it does matter in terms of units. So are we good on that one, or are there questions? All right, I'm going to assume we're good. So y'all ain't talking to me. But this is really important. It may seem kind of simple, but this is the center piece for all of the stoichiometry problems that we're going to be doing from here on out for the rest of the chapter. So if this doesn't make sense to you, then when we add on to the calculation, it's going to become even more confusing. So I want you to do one more on your own, and then we'll start doing some real stoichiometry problems. This time we've got hydrogen chloride gas and chlorine gas. Those are the 2 things that we're interested in. So go ahead and give this a shot. I'll give you another 2 minutes, and then I'll start setting it up. You can put your answer in the chat, Once you get an answer, I'll start setting up the problem. So we've got 0.750 moles of chlorine gas. And we're trying to figure out how many moles of hydrogen chloride gas we're going to produce. We need to use a mole ratio that talks about the chlorine gas and the HCl. We're going to put the moles of HCl on top and the moles of chlorine gas on the bottom. So you should get 1.5. With sig figs, you got to put 1.50. How do we feel about these so far? All right. Now we're going to start doing some stoichiometry problems. That was just the warm-up, okay? There's 3 types of stoichiometry problems. We're going to start with mass to mass. So that means that you're taking the mass of one reactant or product and converting that to mass of another reactant or product within the same chemical equation. I think it's best to just see an example, so that's what I'm going to do. This is the same example that I used in the YouTube video. I wanted it to be in 2 places so that if you have questions, you can ask me during class. And then if you watch the lecture that's already posted, then you kind of already have an idea of what's coming. So let's do it. What is the mass of mercury produced from the decomposition of 1.25 grams of orange mercury 2 oxide? So we've been using this chemical equation for a bit. And I like it because I can make a lot of questions from it. The question is asking us about the mass of mercury, and we're given a mass to start with. So you're not going to have a nice little title that tells you it's a mass to mass problem. You need to figure that out. And that's why I like to write out what I'm given and what the question is. Now I can identify, okay, 1.25 grams, that's a mass. And I'm being asked about what another mass is. So always take the time to figure out what type of question you have, because by the end of this, we're going to have 3 types of stoichiometry problems to do, and they all have different ways of solving them. The first example is mass to mass. To go from mass to moles and moles to mass, you always need molar mass. The molar mass of the mercury 2 oxide has already been provided. That will not always be the case. The molar mass of mercury, you just have to look at the periodic table. So we haven't done anything crazy yet. We're just setting up our molar masses. Now I'm going to set up kind of the flow of what our plan is to get from the mass of mercury 2 oxide to the mass of mercury. So we're starting with the mass of mercury 2 oxide. We need to get that to moles. The way you do that is using the molar mass. Now that we've got moles, we can use a mole ratio to get to the number of moles of mercury. And the final step is to get to grams of mercury using the molar mass. So I'll try to stick with the same color scheme so you can match up which unit factor goes where. We've got our mercury 2 oxide. Oh, no. Ooh, I thought I lost it for a second. Okay. So the first piece, we have to write out a unit factor to go from grams to moles of mercury 2 oxide. That's where the molar mass comes in. Now we need a mole ratio. What mole ratio do I need to use here? You can put it in the chat. We're going from mercury 2 oxide to mercury. If we're going from mercury 2 oxide to mercury, we need to use those coefficients to write a mole ratio. So what's our mole ratio going to look like? Thank you. It's going to be 2 to 2. The last part is using the molar mass of mercury to convert the moles of mercury to grams. Go through and do your unit analysis. The first step, we're trying to get to moles of mercury 2 oxide, and that's what we did. The second step, we're canceling out those moles using a mole ratio to get to moles of mercury, and that matches up. The final step, we're using the molar mass of mercury to get to grams. Try putting this into your calculator and tell me what you get for the mass of mercury. Yes, that is what I got to. So make sure that you can put all this into your calculator and that you're dividing when you see a number in the denominator and you're multiplying when you see something in the numerator. So that's our example for a mass-to-mass problem. You're taking the mass of one reactant or product and converting it to the mass of another reactant or product. And we're using molar mass and mole ratios along the way. I'm going to go through another problem. I'm going to ask for some input from you guys, okay? So get ready. What is the mass of oxygen produced from the decomposition of 3.85 grams of orange mercury 2 oxide? So we know it's a mass-to-mass problem because we're starting with grams and the question is asking about grams. But this time, we're trying to figure out how many grams of oxygen we're making. We still know the molar mass of the mercury 2 oxide. For the molar mass of oxygen gas, I'm going to use 32 here because it's so close. Our plan is the same. How do we convert from grams of mercury 2 oxide to moles of mercury 2 oxide? What do we have to use? Molar mass. Now we've got to go from moles of mercury 2 oxide to oxygen gas. What are we going to use for that? That's what we were just working on. We need a mole ratio, okay? So you use a molar mass, then we have to use a mole ratio to go from moles of one reactant or product to another. Then we go from moles of oxygen gas to grams of oxygen gas. And again, we're using a molar mass here. Where am I putting my grams in the molar mass, the top or the bottom? We're going from grams to moles. So am I putting the grams in the top or the bottom? Thank you. If you're struggling, don't just be quiet or say somebody else will answer. Let me know. If you're stuck, if you're like, I really don't get it, just say something. What's our mole ratio going to be? We're trying to go from mercury 2 oxide to oxygen. What's that mole ratio? Almost. What's the coefficient for the oxygen? That's a 1. When we write it, we need the 1 on top, because that's moles of oxygen. So this is where it really counts, because it's not just a 1-to-1 relationship. So that 1 mole of oxygen gas goes in the top, the 2 moles of mercury 2 oxide goes in the bottom, because we're trying to cancel that out. The final piece is using the molar mass again, but this time it's for oxygen gas. When you put all this into your calculator, we'll try it. What do you get? We need 3 sig figs here, so 0.284 grams of oxygen gas. Alright, I'm gonna give y'all a break. Shake your brain out. Come back ready, because after the break, I'm gonna have you try your own. So it's about to be 9:26. Let's take a 10-minute break. So we'll break till 9:36. Come back ready. All right, everybody, it's 9:36. Time to get back to it. Still working on these mass-to-mass problems here. And now it's time for you to try it yourself. So I'm going to give you 5 minutes to set up the problem and get started. If you get stuck, let me know. Don't just be quiet, but let me know. It's really okay. Give it a shot, and if you get stuck, let me know. If you get to an answer, you can put that in the chat. But just kind of let me know how you're doing. Even if it's hey, I don't know if I feel comfortable trying it yet, I'm still learning. That's fine too. Just give me some kind of feedback, and that will help. So 5 minutes, and then I'll check back with you. Alrighty. By a show of hands, how many people are stuck? Don't be shy. It's okay. You're just learning it. If there's one person, then I'm assuming that there's many more. Okay. Okay. So here we go. Doing these problems, it's a process. Thank you. Thank you for letting me know. Doing these problems, it's a process. And I'm showing the process to you over and over and over again. You're going to have to practice. That's just what it is for these problems. The first thing you do is figure out what is the question. We're looking for the mass of mercury 2 oxide decomposed to yield 25 grams of mercury. So when we write our question over again, that's what we're looking for. Now we have to go to the plan. And this is the part that you need to know and understand. That we're going to go from the grams of mercury to moles of mercury and how do you go from grams to moles? It's always the same. How do you go from grams to moles? Molar mass. In this case, we need the molar mass of mercury. So don't forget that part. What comes next is we have to take those moles of mercury and figure out how many moles of our unknown, which is mercury 2 oxide in this case. How do we go from moles of one substance to moles of another in the same chemical reaction? We need a mole ratio. What's the last step? We have moles of mercury 2 oxide. What are we trying to get to? We're trying to get to grams. And we're going to use that molar mass. Only this time it's the molar mass of mercury 2 oxide. So if we want to put it in more generic terms, we're starting with grams of A. We convert to moles of A using the molar mass. We convert moles of A to moles of B using a mole ratio of B over A. And that's from that chemical equation. The last part is converting from moles of B to grams of B using the molar mass of B. And if we were to classify which is A and which is B in this case, the A would be the grams of mercury, and the B is grams of mercury 2 oxide. That's our generic formula for mass-to-mass problems. So let's put some numbers to it. We're starting with 25 grams of mercury. We need to use a molar mass. Am I putting the grams in the molar mass on the top or the bottom? And the way that these unit factors are arranged, where the grams are, where, moles of A, moles of B, it's always the same. The numbers just change. Now we need a mole ratio. And we're looking at mercury and mercury 2 oxide. It's 2 to 2, we know that. But we need the 2 moles of mercury 2 oxide on the top. That way, our units will cancel out. The last piece is using the molar mass of the mercury 2 oxide. When you do all that math, you should get 27.0 grams. So talk to me. I know some of us were still a little lost and confused. Can you tell me about where you got lost? Okay, that's a good place to be. That's a good place to be, since we just did it. Anybody else is if I know where you're getting stuck, then I can help you. Okay, so setting up the equation. So hopefully that generic kind of A to B will help you in setting it up. Are there any other questions? We have other types to try, and I'm pretty much just going to be giving you kind of the formula of how to do it for each of these problem types. What we don't finish this week, we'll finish next week, and we'll do more practice. So between this week and next week, I know you have an exam, but you'll definitely want to try some of these problems and make sure that when you're getting it into your notebook or you're watching the YouTube lecture, that it makes more sense to you, because next week we're going to jump back into it. So I think we should move on to the next problem type. Let this marinate. I'll be posting some practice problems. There's no chapter check-in because you have an exam this week. And there's no mastering chemistry due this week either. So you'll have time to just kind of work on it in the meantime and in between time. So we did mass to mass. Now we're going to do mass to volume stoichiometry problems. That means that we're going to be doing problems that involve gases. So here's our example. How many liters of hydrogen are produced from the reaction of 0.165 grams of aluminum metal with dilute hydrochloric acid at STP? Whenever you see at STP, that clues you in that there's something about a gas. To set up our given and question, the number we're given is a mass of aluminum. The question is asking about how many liters of hydrogen gas. When you read through the problem and you set up what your given information is and what units your question is asking for, that helps you to identify the problem. You know, grams, that means a mass. Liters measures volume. So it's a mass to volume problem. Just like before, we have to go from what we have to moles, and then moles of what we know about to moles of what we don't know about, and then we get to our final unit, which in this case is liters. So here's the generic how you solve it. We're starting with grams of A. We need to get to moles of A. Always use the molar mass. To go from moles of A to moles of B, it's going to be a mole ratio. This looks the same so far. Where it differs is, since we're talking about a gas and liters, we need to change our moles of gas to liters of gas. And to do that, we need molar volume. With our example here, the aluminum is the A, and hydrogen gas is the B. So I'll quickly rewrite our plan. So you can see how that works out. So that's what we have to do. Now let's write a couple more things out that we need. We need the molar mass of aluminum. If you have your periodic table, look it up. What's the molar mass? You were on it. It was like you were waiting for me to ask that question. We also need to handle this molar volume business. So this is from chapter 8. One mole of gas is equal to 22.4 liters. Now we've got all that out of the way, we need to actually set up the problem. We're starting with 0.165 grams of aluminum. Now we need to set up our molar mass. Same as before. What's our mole ratio going to be? Remember that we need to be able to cancel out the moles of aluminum. So the moles of aluminum need to go on the bottom. So it's going to be 3 to 2. 3 moles of hydrogen gas over 2 moles of aluminum. And in the generic one, I told you, mole ratio, it's B over A. Our B in this problem is hydrogen gas. So this part is for real. So you just have to write the number of moles of B over the number of moles of A. Then the last part is molar volume. We're trying to get rid of the moles of hydrogen gas. So from our unit equation here, we're going to put that 1 mole of hydrogen gas at the bottom and the 22.4 liters at the top. When you're doing a mass to volume problem, this is always the orientation of your molar volume unit factor. The 22.4 liters on top, 1 mole on the bottom. When you do this math, you should get 0.205 liters of hydrogen gas. Make sure that you have the generic how it's done in your notebook. That will help you. Are there any questions, or should we go on and try another one together? So let's try another one. How many liters of oxygen gas are produced from the decomposition of 14.6 grams of sodium chlorate? We're starting with the mass. And we're asked about a volume. So that makes this a mass to volume problem. Make sure you identify the problem type before you start writing everything out, because it'll help you know which problem type you're solving so you can pull the right unit factors. We're going to need the molar mass of sodium chlorate. Take a minute and figure out what that molar mass is and put it in the chat. So I agree with that. That's what I have. Now we're ready to set up the problem. We'll start by writing out the plan. We're going to go from the mass to moles using the molar mass of sodium chlorate. We already figured that out, so that should be a snap. Next, we have to go from moles of sodium chlorate to moles of oxygen. That means we'll need a mole ratio to get us from one to the other. Then we need to go from moles of oxygen gas to liters. We're going to use molar volume here. This is our first part, getting to moles. The second part is the mole ratio. I want you to tell me what the mole ratio is. 3 to 2. 3 moles of oxygen gas. Because remember, our A and B, it's B over A. So 3 moles of oxygen gas, 2 moles of sodium chlorate. The final part of the equation, we're using molar volume. And it's always going to be that 22.4 liters over 1 mole when we're doing mass to volume. First step, we went to moles. Second step, we went to moles of oxygen. Third step, liters of oxygen. On an exam, the most important part to me is you being able to set this up. So if you fumble a number on a calculator, you're not going to lose that much in terms of credit. But you're going to get credit for each of these unit factors that you set up properly. And it's the same way for the Chapter 8 questions, where you have to convert from atoms to mass or something like that. The most important part is setting up the equation. If you can't do that, then you're not going to get the right answer. Or it's very unlikely that you will. So here's what we're going to do. I've got another problem that I want you to try. Try that, we'll go over it, and then we'll stop it here for this week. So it's another mass to volume, and I'll get you started. We've got some mass of sodium chlorate that's decomposed to yield 30 grams of sodium chloride. How many liters of oxygen gas were produced? And we're assuming STP here. The sodium chloride is your A. The liters of oxygen gas, that's your B. Try setting this up. I'll give you 5 minutes, and then I'll come in and start setting up the problem. But use that generic, grams of A to liters of B that I gave you to try setting up the problem. Alrighty. Did we get to setting up an equation? Did we get stuck? How are we doing? Let me hear from a few more people. Did we get stuck? Do we feel intimidated? What's going on? All right. So I'm going to set up the problem. So I didn't give you the molar mass of sodium chloride, but that's something that you should be able to figure out. So that's what your equation should look like. We're using the molar mass of sodium chloride, then a mole ratio, and then molar volume. When you do all that math, you should get 17.2 liters of oxygen gas. So how was that one? Did anybody get that answer? Good. So like I said, we're going to stop it here. I'm going to jump to my reminders, because we're not going to get through. Okay. So, you have an exam this week. It's on chapters 7 and 8. It is going to be take home. It'll be posted on Wednesday. You have to upload your exam before the end of the deadline. So, your exam must be uploaded by 11:59 p.m. on Friday, October 30th. If it is not, you will get a 0. So don't go to download it at 11:59 p.m. It needs to be uploaded and on Blackboard at that time. Please make sure that you actually submit it and that it's in a format that I can read. Make sure it's a PDF. If I can't open it on Blackboard, I can't grade it. So please, 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 don't just upload any old thing. Double check it. Make sure that it is a good document, that it can be read, that it's not too small, it's not some weird format. It's the same thing that we do for the chapter check-ins. So double check that. You do not want to get a 0 on an exam because I can't open it. I will let you know, hey, can't open this until you send me something else, you get a 0. Send it to me by this date. If you don't check your course messages, if you don't look at the feedback on Blackboard, you're not going to see that. So make sure that you check Blackboard just like I do. No office hours next week. So this week we've got office hours Wednesday 2 to 4. You can set up meetings, individual meetings if you need to on Wednesday. But next week, Monday, Tuesday, I teach. And then after that, that's my family time. So please remember that and respect that. I will not be checking course messages. I will not be checking email. You won't have any assignments due. Just give me that space, and I really appreciate it. Your Master in Chemistry for Chapter 9 is due Sunday, November 15th. So we will have already gone over the rest of Chapter 9, and you'll have time to ask questions in office hours before the assignment is due. That's all I have for you. If you have any questions, you can throw it in the chat or stay behind. If you have already set up a meeting with me to chat after class, just stick around and we can do that. So, it's up to you. Go ahead. Yes, correct. There's still going to be a folder for exam 4. And it's going to have a PDF and the Word document, just like I do for the chapter check-ins. Print it out. So I will tell you everything about where to upload it. So I want you to upload it just like you do with your chapter check-ins. Upload it through Blackboard and make clear what your answers are and show all of your work. You're welcome.